This is a quick review of Chapter 6. Brown-Lemay-Burston in Chapter 6 focuses on the electron, where the electron probably is, describes where the electron probably is, and gives a bit of a background about how we know where the electron probably is. Make sure you have a paper, pen, and book in front of you before you begin this video cast. Pause the video now to make sure you have a paper, pen, and book. The electron. The electron resides outside of the nucleus. The electron is not a particle, although we think of it as a small piece of matter. And it's not necessarily a wave, like a light wave, but it's actually a mix between the two. And some people call it a wavicle, because it's a particle and a wave together. This is difficult to comprehend. There's mathematics that describes the particle and wave nature of the electron. That's beyond the scope of the class. Therefore, we can probably say where the electron is, because you can't just pinpoint and say there's this speck electron somewhere. That's a particle. And you can't say it's just like a flowing wave through the ocean, but we can probably say where the electron most likely is. This volume, or this space where electrons probably are, have a special name. They're called orbitals, or an orbital, O-R-B-I-T-A-L. Don't confuse that with an orbit, like the Earth going around the sun. An orbital is actually a physical, three-dimensional space that describes where the electron probably is. Another way that's used for this orbital is a probability map, or a 3D graph of where electrons probably are. And there are 4 different known types of probability zones or probability maps of where electrons probably are. The first one is called S, as in sphere, and it has a spherical shape, and it looks just like a sphere. You can see these in your book right here. This is a 1s orbital, a 2s orbital, a 3s orbital. And notice as the number gets bigger, the sphere size gets bigger. And as you move away from the nucleus, you can actually look at the graphs that show the probability of an electron being in a certain zone gets higher in certain areas, giving rise to, hey, there's probably an electron in this area called the 1s zone, this area called the 2s, and this area called the 3s. Another nice, really good picture of this is here where you have like a shell, and then it's peeled away, and you can see this area right here would be probably where the sphere of the 1s would be, and this area would be where the 2s, and this area would be where the 3s is. And you can see these little white lines in between here that are called nodes. There are areas where electrons would not be. These are areas where for sure they're probably not. Everywhere else they could be, and where it's the darkest blue in these areas, that's where the electrons most likely are. They have like a 90% chance of being in that area. So S's are spheres, and they're a probability zone of where electrons most likely are. The p orbitals are actually shaped kind of like dumbbells. And you can see these in some much better pictures than I can draw right here. They're kind of fuzzy like this when drawn, because as you move further away from the center, there's less and less chance that the electron is there. Remember, it's in 3 dimensions as well, so you can actually think of it kind of a dumbbell shape like this, and then very, very likely that they exist inside some of this area called a probability zone or probability map. You'll notice that it has a px, a py, and a pz orientation, and 2 electrons can fit in each one of these orbitals. The 2 could be both up in this area at 1 second, and then 1 could be here and 1 could be down here. You just don't know for sure. You just know that they're probably in that area or that zone sometime. Just as with the s orbitals, there can be 2 electrons in each s orbital as well. So 2 in the 1s orbital, 2 in the 2s, 2 in the 3s. Each orbital can hold 2 electrons at a time. The next orbitals are called the d orbitals, and there are actually 5 different d orbitals, 5 different orientations. You can notice these are kind of like flower petals, and they exist in different planes. As you can see, it tries to draw really nicely with colors here. And then there's the one that's the donut shaped right here as well. And the 2 electrons could exist here, or maybe 1 in the donut and 1 down below, or maybe 2 in the donuts at one instant in time. We're not sure. We just know that this 3-dimensional map, which is actually described by mathematics and is a graph of that equation that describes where it is, holds 2, or has the possibility of holding 2 electrons. So the P's are shaped like dumbbells, the D's are kind of like flower petals. And it's really important to remember that there is 1 s orbital in each what's called energy level. There are 3 of the P-shaped orbitals, 1 in the X orientation, 1 in the Y orientation, and then 1 in the Z orientation. I'm not doing a very good job of drawing 3-dimensionally there, but if you do a 3-dimensional space like this with X, Y, and Z being into the paper, you can think of 1 relating on each one of those. And then the flower petal ones, remember there are 5 orbitals for that, so maybe you can see a pattern. The S's have 1 orbital, the P's have 3, the D's have 5, and if you make an educated guess, the F's have 7 orbitals. And they have flower petal shapes as well, except they have 7 different shapes and 7 different orientations. And if you remember, each orbital can hold 2 electrons, so an S orbital area could have 2 total electrons. The p orbital, or the p orbitals, of which there are 3, could each hold 2 electrons, so they could hold 2, 4, 6 electrons total, 2 in each orbital. The flower-petaled orbitals, or known as the d, again, have 5 orbitals, 2 in each orbital, so they could have 10 electrons. And maybe you see another pattern emerging here, 2, 6, 10, 7 orbitals here, 2 in each orbital, so you could have 14 electrons there total in what's called the F set of orbitals, also known as a sublevel. So now we can describe these orbitals in 2 ways. We can describe the orbitals in terms of distance the electrons are from the nucleus, also known as the energy level that those orbitals are in. And then we can also describe them in terms of the specific shape that we just talked about, the orbital. We describe both of these things by using a symbolism called electron configuration. Electron configuration is a handy way to say, hey, these electrons reside closer or further away from the nucleus and are organized into certain patterns. If you look in your book, there's actually a really nice diagram here showing how the energy orbitals go from 1s to 2s to 2p to 3s to 3p to 4s to 3d to 4p. And I'll describe what each one of those little boxes means as well. So electron configuration symbolizes 2 things. It symbolizes 1, the distance the electrons are from the nucleus, and secondly, the orbital or probability zone. The way that electron configuration is written is by writing a number for the distance from the nucleus, also known as the energy level, and then using the S, P, D, or F configuration to indicate the sublevels orbitals, in this case the S, and then a superscript to indicate how many electrons exist in that particular sublevels orbitals. In this case, it's pronounced 1s2 and could also be written as a box with 2 arrows, one with what's called an up spin and one with a down spin. Each arrow represents an electron, and there are a total of 2 electrons in the 1s energy level. This is known as the lowest energy level, closest to the nucleus for any electrons. The next energy level would be the 2s electrons and could be symbolized as 2s2. Once again, could be symbolized with a box or with a line with 1 arrow in the up direction, 1 in the down direction. The next energy level we encounter is the 2p energy level. You don't have to write the 2 again if you want, but this electron configuration describes 6 different electrons that could exist in the 3p orbitals, 3 total p orbitals in the 2p sublevel. And this time you'd want to write 3 different boxes here, one for each p orbital. Remember, there's an x orientation, a y orientation, and a z orientation. 1 electron would go in each orbital before they start to pair up. And notice each orbital has to have an electron of the same spin, same direction of arrow, before they start to pair up. And then we'd finish or complete the second energy level. This is the first energy level, the second energy level, each energy level indicating how far away from the nucleus you are. Next would be the third energy level, with S being the sublevel, and the S-shaped orbital once again could hold 2 electrons, 1 box, one with an up spin, 1 electron with a down spin. Then there would be the 3p orbitals, and this could hold 6 electrons once again, 3 boxes again, 1 in each orbital before they start to pair up. And then there would be the 4s orbitals that would show up. Anyway, one of the handiest ways to fit all of this electron configuration into your brain is not necessarily just to memorize 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but to fit it into the periodic table. And the periodic table is actually organized according to the way these electron configurations are set up. In your textbook, there's a really nice orientation of it right here, where they show the s orbitals right here in the first 2 columns, being the alkali earth and the alkali earth metals, and then the alkali metals and alkali earths. Then the transition metals are the d orbital containing electrons. The p orbital containing electrons are over here in the other set of the representative elements. The representative elements are the s and the p blocks together. Notice 1s and 1s are just 2 elements up here, hydrogen and helium, and then the f blocks actually are represented down here below in the rare earth elements. So how does this fit into your periodic table? If you've got a periodic table handy, you can draw one like this, just like this, or you can just take out a periodic table, and I'm going to draw all over it to illustrate how the electron configuration works. Remember, this is the 1s right here. This is all the s orbitals right in here. This is the p's. Whoops, I'm sorry. This is the d orbitals right here. This is the p's right here, not including helium. Remember, helium is also part of the s orbitals right here. And then these are the f orbitals down here. And writing the electron configuration for hydrogen and helium would be 1s2, and it would be 2 electrons. Hydrogen, helium, this would be the electron configuration for helium. If we wanted to go on further to beryllium, it would be 2s2, 2 more electrons. This would be the electron configuration for beryllium. Skipping across this valley right now, you come to 2p6. 1, 2, 3, 4, 5, 6 would give you the electron configuration for neon. 1 electron in each orbital before they start to pair up. This would be the electron configuration for the noble gas neon. Continuing on, coming back here, this would be the 3s orbitals, and there are 1, 2 electrons there. This would be the electron configuration for magnesium. Skipping across the valley now, we encounter the 3p orbitals, which includes 1, 2, 3, 4, 5, 6. And if I just drew 3 electrons, 1, 2, 3, all of the same spin, I'd be at the element phosphorus. If I added 3 more electrons, 1, 2, 3, I'd now be at the element argon right here. And this would be the electron configuration for the noble gas argon. Sometimes what periodic tables will do will base the electron configuration after a noble gas upon that noble gas configuration, and they'll simply write the noble gas in brackets and then write the next portion of the electron configuration for an element after the brackets. So for an element, say like nickel, for example, you could write argon's configuration, and then after argon would be 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8. And notice I said 3, because the third energy level also contains Ds, but since they're of higher energy, they fill after the 4s electrons. And so the 4s electrons fill first, and then these are actually one energy level less than what their period number is. So this is the 3d, the 4d, and the 5d, and the 6d. And not surprisingly, there are some exceptions down here for the Fs as well. Even though the Fs fit right in here and right in here, they're 2 energy levels less. 2 energy levels less than their period number. So this is actually the 4Fs, and this is the 5Fs right here. Using these electron configurations, you can write where the electrons probably are for any element on the periodic table. And if you take a moment and take a look at your textbook, you'll also find a few exceptions to these electron configurations. Notice strange ones like copper that look like they should be 3d9, but really they're 3d10 4s1. And then you'll also notice a couple of exceptions in silver, chromium, and molybdenum. And why these exceptions happen actually isn't that unusual, just because of how close the electron energies are to one another. The entirety of the periodic table's electron configurations are based upon the energy and how much energy it takes to have those electrons move further and further and further away from the positively charged nucleus. The more down on the periodic table we move, the further the electrons are from the nucleus, and therefore the more energy it takes to keep those even around inside of the atom, and the less attraction there is from the nucleus, and therefore the more reactive these elements down here on the periodic table are. This has been a quick review of Chapter 6. More on using these electron configurations in Chapter 7. And just a little bit of background will happen in the course as well about why we know these electron configurations actually exist. Good luck with your Chapter 6 problems.